based on their originals. Do I need to explain this?
Wait, so is this credited to anyone specifically?
Pardon me?
It's just
It's credited combined.
It's called
the combination of three guys.
because
There's no personal
the
credit.
work of these four
There's no name for this one that you need to know.
the work of these four scientists
There's three.
is combined.
Avogadro is in the next. Is for the.
Yeah, Guy, Lusac,
The two
Charles,
people,
and Boyle.
Nathan.
Got it,
Two
guys.
people.
So
Wait, okay, so the combined takes all three of those laws and applies them at the same time.
right.
Then
So
why even have them? Why do you need to know them separately if you know
Well,
the
because
combined?
we're talking about the order in which they're discovered scientifically, right? Or like historically, I guess.
and it's not always practical to use the combined one if you know one's constant.
Yeah.
So like with a balloon, the pressure inside and outside have to be equal, otherwise the balloon explodes. So it'll expand and contract with temperature.
I don't remember the order in which they were discovered, but around the same time, Boyles, Charles, and Guy and Lusac kind of came up with those laws, and then someone after them was like, "Hey, we can combine them," and then someone after them, well, Nathan will show you.
All right. So this is fairly simple, just based off
So
the earlier
don't
things.
care too much about combined, okay?
You going to Avogadro?
Yeah, I'm gonna do
Do Avogadro, then do ideal. Ideal is the one you really.
Hashtag swag.
Avogadro, besides having his awesome number.
What do you guys know about Avogadro actually?
What?
Tim,
Has anyone ever heard that name before? Sounds like
Yeah.
avocado.
Tim.
Rishi has. Rishi,
Tim.
who's Avogadro?
what do you guys know about Avogadro?
His constant 6.02 times 10 to the 23rd.
What does that
Okay,
mean?
what
does
is
that
that?
do?
That's how many particles or atoms or et cetera, et cetera, et cetera there
What do you
are
mean?
in one
Wait,
mole.
Particles, not particles.
So,
Particles.
the
Or
you want me to
atoms
explain
or
Molecules.
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 There's like 4 different things.
Molecules
So
is
the-
the widest term. It's the
so,
most confusing.
Osman.
Explain it.
Okay, so we measure the weight of, say, one molecule in atomic mass units. That's basically pretty close to just a count of the number of protons and neutrons inside an atom. And all of those together will give you the total mass of whatever thing you're dealing with. Those are really, really, really tiny. It's an order of magnitude of 23 smaller than a gram. So to get that into a range that humans can start working with, we use something called a mole, which is the number of particles of, let's say, number of molecules of sugar or of carbon dioxide, number of molecules of carbon dioxide, so that the numerical value of the mass in grams for 1 mole of that many is equal to the numerical value for the mass in AMU, or atomic mass units, for 1 molecule. So it's equal, Avogadro's constant, big N subscript big A, is equal to 6.02 times 10 to the 23. Molecules or formula units or ions
Molecules
or
is
particles in general per mole. So that's a count of how many are in 1 mole to make those numbers the same.
And really, this is just like an accounting thing. It's no, it's just.
It's to bring it down into.
There's
usable
no
numbers.
unit conversion over here. There's no dimension conversion over here. It's just you're accounting for a number.
Right. It's just putting it into numbers that are more usable than like 6.
So
times
it's
10 to
just
the
a
23.
scaling factor.
Yeah.
Yeah.
All right. So N, you need to know, this stands for number of moles.
Lowercase n.
Lowercase n. Capital N is number of molecules. But you won't use that till later. Alright, and this one actually assumes 2 constants, but should be N over V. I guess it's V over N or N over V works. N over V equals N over V. And V is still volume. So what are the 2 things that you're assuming are constant in this situation?
temperature and pressure.
Yeah.
Right.
So
So this is saying, nice. This is saying that whatever particles you had inside your measurement area or volume, you're still going to have inside later after that volume changes.
alright, so what's the graph of this look like? If we've got N on bottom and V on the side.
So this is assuming, I think, uniform density.
No, you pressure and temperature.
Pressure.
Uniform pressure intensity.
Right.
Because
We just
it would
said
actually
gas.
be not uniform density.
All right, guys. So
Yeah,
what
it's
is
free.
the
I mean, yeah, sorry.
So this is also uniform density.
what does the graph of it look like?
Density would be your
Straight line.
Straight line, straight being that kind of line.
Yeah.
We could have like straight line going.
So
down and
if you have uniform density,
Okay.
gas area, field, whatever, and you expand the area you're looking at, there should be the same. Like there should be a relevant increase in the number of particles.
So I've got an example for this. Let's say you put a bag over this, right? And then you turn this on. That would be like pouring gas molecules into the bag, right?
Well, yeah.
And the bag would start to expand because it's getting gas inside it. So that would be what this is. It's getting more of the molecules in it, therefore its volume expands.
Temperature doesn't change, and pressure doesn't change.
if you breathe into a paper bag.
Yeah.
Same concept.
Same kind of thing.
So
Just
this is
putting
just-
more stuff into it will increase the volume. That makes a lot of sense, right? And they're just directly proportional. Any questions?
Is there any good way to remember this?
Well, Avogadro, Avogadro deals with moles and
He's the mole
molecules,
man.
right? So if you see anything, it's like the only law exclusively dealing with moles and volume. So
So this is essentially more stuff takes up more space.
notice that all these laws that have names attached to them, they deal with 2 dimensions only, right?
Yeah. So everything else is held constant. You're seeing how one thing varies with another thing changes.
Right. Now, ideal is where it comes in.
All right.
Wait, Nathan.
Mhm.
Maybe this is okay. So in your example, like your balloon is filling up
Right.
with gas molecules,
Right.
but won't at one point your balloon get like too much and it just explodes? Because it's too much. So wouldn't that mean it's pressure increase?
I wasn't saying a balloon. I was saying a
Oh.
like a bag, just a
Oh,
bag.
man,
Yeah.
balloon.
So,
Anyways, your bag.
If you had a balloon, and I'm holding a balloon, and there's 1 atmosphere pressure outside, and the balloon is no longer changing, what is the pressure of the balloon inside?
It's 1.
1 atmosphere. So if I put more air in, it's going to expand, right?
Well, Jack,
So what's the pressure inside now?
Still 1.
Still 1 atmosphere. So the pressure never changes.
we're talking about a balloon that infinitely expands without having. We're not gonna. There are no pressure changes.
We're
There's
talking about the
there's
perfect bubble
elasticity.
gum.
Yeah.
Yeah.
There's like we're saying there's no like. We're not saying that there's a cap to how big it can become.
Oh, okay.
Okay. Like a balloon, you're capped by like elasticity factors and all like sorts of things that happen.
And even if there were a cap like that, then you just have a line segment on your graph. And you're saying that this is the, as long as the balloon is intact, this is the relationship that it has.
And you stop. You can't add any more molecules to it.
Oh, okay. I got you.
Are you picking up what we're putting down?
Anything
Yeah,
else
yeah.
about
I am
Avogadro's
picking
law?
it up.
Unit, right?
Those guys.
Yeah.
So,
Okay. Then do ideal.
right.
Oh. All right. I'm sorry.
All right. So all of these laws, including
He's all over this like
Avogadro's
sticky on
law,
cat litter.
This,
combine.
so if you're writing anything down at all, this is a law to write down. This is like golden.
Okay.
This is the
Yeah, it's from these
The
laws that
golden
we
rule
do
for
a
gas
lot
is
of the
zero.
later stuff.
The golden rule for gas.
Gas law. Wow. Wow.
All right.
Ideal gas
Should I write
because
it?
you're assuming the gas behaves ideally. And Nathan and Jack will explain what that means.
Pressure, volume.
Yeah.
I'll do it over temperature because that's how they've been doing it so far.
Or you could just PV equals R. That's easy to remember.
Oh yeah. Okay. Perfect.
Yeah.
All right. PV equals N T, but then there's this R over here.
Oh, you did NTR.
It's NRT. Come on,
It doesn't
Nathan.
matter, guys.
Yes, it does.
It just looks better.
I'm
as
just
purple.
using this thing.
We're using NRT right here, Nathan.
So what we know from this is with all of the other laws, we put them together. Pressure and volume vary inversely, and temperature and the amount of stuff.
NRT.
Wait, I'm gonna explain why. Can I explain?
Yeah,
Go ahead.
let him explain why.
So,
First off, mathematically, that's just how the equations add together.
so
with
first
some
you can say
constant.
pressure volume is proportional to NT.
That alpha means proportional.
Right. Because you got pressure volume over NT equals pressure volume over NT. Right? So if you assume this is like 1,
Or constant.
or we'll just stick a constant in here, then you do PV equals K in T. In this K, we actually have a number for this K since we know the units of everything else, and we call it R. because R is the universal gas constant.
It's going to be like a proportionality constant to make your numbers work out nicely and your units work too.
Gas has one S, guys.
There are multiple R's. If you look at your UIL sheet right here, the formulas, it'll be under, let's say the gas constant, universal gas constant. It'll give you the symbol R and the value. This will change depending on what you're using it for. If you're using it for gases exclusively, you'll probably use 0.0821 liters per atmosphere per mole Kelvin. Those are the standard values. If you're talking about energy and its relation to like work done on the gas, maybe you'll do 8.314. And just make sure your units work out. So you see right here. See right here where it says joules per mole per Kelvin or liters per atmosphere per mole Kelvin. Make sure whatever units you're using, if you're using liters per volume, use that gas constant, okay? If you're using atmospheres per pressure, use that gas constant. And so here you can see that again.
And the actual source of this gas constant, this one uses moles, but this comes from something called the Boltzmann constant. So there's this guy, Boltzmann. I'm just going to explain this one thing. And then I think we go to break. You don't have anything more?
No, I've got Vanderbilt.
Okay. Let me explain Boltzmann constant. So, Boltzmann, he did a lot of this research in thermodynamics with individual things. And he was a physicist, so he looked at one atom. Chemists like to look at two. So, he was looking at just individual molecules and realized that he basically worked out all the same stuff just in regards to molecules. So he found the value of the constant for this whole thing to work out with, instead of moles, you just use the count of all of the molecules interacting in your area. So what you end up having is nR equals big N kb. And since n is just equal to the number of molecules divided by Avogadro's constant, then you get kb equaling r times basically the number of moles per number of molecules, which is equal to r times Avogadro's constant. Or if you were to put that backwards, R comes from comes from the Boltzmann constant divided by Avogadro's constant.
By Steffi's.
You really won't see anything else about Boltzmann until physics with all the thermodynamic stuff. That's all I had to say about that.
And that's all I have to say. Let's put the ideal gas law over here.
Yeah.
Okay.
The ideal gas law is super important.
So this is the ideal gas law. You'll be doing most of your stuff in here. But
P equals nRT.
there's a reason it's not just the gas law, right? It's the ideal gas law. And you know, nothing in life is actually ideal.
And they're
I'll
not
just
saying
tell
it,
to
they're
you
not
now.
calling it the ideal gas law because it's just one equation for all those four equations. That's not why it's ideal. It's ideal because it's an ideal gas. And so it's not going to be, we're saying it behaves ideally. In a perfect world, this is how the gas would behave. That's why it's the ideal gas law. It's not the ideal gas
I
law.
want to explain the concept.
Yeah,
for you.
the distinction right there?
Why that makes things
Okay.
weird.
Okay, so it's ideal gases, not the gas law that is the ideal.
So for now, we're just warning you that it's not ideal, and we're going to cover kinetic molecular theory,
What?
and then we're going to explain.
T?
Okay.
So, yeah, in